first, but no, first let me open it. So joint presentation between me and Manu. So we have 45 days. And actually, so it's about the state of the art and major challenges in wearable and collaborative robots. Okay? Yes, and I think the first half of this presentation, of course, I will give the presentation about these wearables, and the second half will be given by Manu, which I will, he will take over after 15 minutes. So pretty much I try to finish within everything within 20 or 15 minutes. So you see my screen, right? I think.
Yes.
Okay. So today's, my main approach in explaining the state of the art and major challenges or bottlenecks is that it's really I find it a little bit challenging, because when it comes to wearable robots, there are so many wearable systems, right? Not just upper limb or lower limb, back exoskeleton today. I think Katya will talk about it. Passive systems and active systems, and so many, right? For example, you can see the left hand side. There's this. Upper limb exoskeleton. In the middle, we have this back support exoskeleton, and at the right, you see a lower body exoskeleton. But what I try to do is that I try to find the common ground in these systems as much as possible. What is the common problems, or what are the technical challenges that apply both wearable systems, regardless of upper body, lower body, or passive or active. Well, passive systems I think will be also mentioned by other mechanical engineers. So I will try to mention the active systems. So the common ground is that there are three aspects. I think, to me, a wearable system must be mechanically transparent. A wearable system must handle physical interactions, and the wearable system should be designed with the human anatomy in mind. So I will start with let's start with a poll. Dennis, could you put the first poll maybe? So a wearable system must be mechanically transparent, and let me give you 1 minute. And what do you understand? What is your understanding regarding the term mechanical transparency? Feel free to choose any options you mind. So imagine you wear this robot, which is shown at the right hand side. It's a exoskeleton I built in Japan when I was a researcher, right? ATR. So what's your understanding? Feel free, don't feel pressures, just you would like to understand. Because I will re-ask the same question and see if we are on the same term.
Are instructors allowed to answer, Barkan Hocam?
No, just the students, exactly.
Okay.
Thanks for pointing out. So we only ask the students, graduate students, and not the instructors. We also have some instructors for their expert feedback. The human robot combined system watches Casper together, so like 3 answers. Yeah, I always put some kind of troll option, because I like to troll myself sometimes. So, Ebru, how many students do you think we have? Or I think it's already 40 out of 51, I think. 41.
Yes.
Okay, should I end polling?
Yeah, I think we should.
Okay, so 41, 80%. Oh, almost 40. So share results, right? Can you see the result? But basically, I'm sharing my screen, so you see the result, right? So a great majority of people choose the robot exerts zero force on the human user, e.g. it carries its own weight and its joints can be moved effortlessly, no friction. Okay, so let's check it out, what I mean. So before mechanical transparency, I would like to explain the backdrivability. So backdrivability roughly represents a system's physical interaction capability. For example, in this GIF, you see a therapist is trying to move a patient's knee joint, right? So this knee joint, sometimes it's harder to move. I think therapists already know if the knee is stiffened. But normally for a healthy person, it's really easy because some systems, are naturally backdrivable. So which means that there's this thing called mechanical impedance, right? You can kind of consider like, if you squeeze all your muscles, basically, you increase the impedance, and in that case, let's say the relative backdrivability decreases. So backdrivability in a nutshell means that how we can move effortlessly, and then, for example, if anybody comes to any person can just freely move your arm as long as you don't stiffen your muscles, right? So basically, what we mean by backdrivability is that if the joint impedance is relatively low, and then it can be moved easily. But what happens in the robots? Basically, we use torque amplifiers, which are called gears. For example, here you see in this GIF, and they increase the joint impedance and friction, and sometimes the position control with high gain controllers also they increase. So which means that it's hard to make them move. So imagine if you wear this wearable system, but you cannot move your limbs because it's so stiff. The robot is reacting. Okay? So maybe I can skip this one. So let me show you a video first. So in this video, for example, my former student from Turkish Technological Institute, so he moves, and you see the robot legs, this wearable robot legs are attached. But when you leave it, basically then, due to friction, of course, it stops. And of course, you can move, so it's somewhat backdrivable, but because of the moment arm of the links. Okay, but what you need to understand is like, when you leave it, then it stops. But if I cancel the friction to increase the backdrivability, for example, you can see that its natural motion is like a pendulum. So it doesn't stop right now. Of course, this is something called software backdrivability, but so right now, what we do here is that, so we somehow cancel out all frictional effects. So if you wear this exoskeleton, of course, you will still feel the gravitational load, but you feel no friction. By the way, the related reference is always given at the bottom. And then, of course, if you wear it, of course, you can move it, but you have to carry the robot weight. But then, what we mean by mechanical transparency is, in addition to friction, the gravity compensation, right? So the robot basically should carry its own weight. For example, in this particular demonstration, you can see that you can see the robot joints, they stop all the configurations. So which means that, when you wear it, you don't feel the gravitational load because it just carries its own weight, and also no friction. So this is somewhat called transparency. But to do so, normally we need to enable something called position control. Maybe I can mention here. And the force control, because the position control, so you might think that, I can give some kind of torque commands and then the robot can move. But here I mentioned that if the motor is powerful, if you give a position command, which means that like if you try to control the position of a joint, you cannot interact it the way that a Japanese student can interact. For example, this is a position control and I try to stop it. This is non-backdrivable. It just doesn't stay. I really try to hold it, but it just, keeps moving and doesn't really respond to physical interaction imposed by me. So that's the whole, then, I was able to stop because the student stopped the experiment. So when we say the transparency, basically this variable system imposes no force, no friction, no gravitational load. So when you wear it, basically you feel like, as if you don't wear anything. Okay? And another thing is also the physical interaction. So maybe we can start the next poll, I think, the second poll. Oh, sorry, not now, sorry, I'm sorry. Let's watch this video. So in this video, we see the former versions of Mindwalker. It's a great exoskeleton built in 2013 in University of Twente, Vander Poorten lab. He's my favorite researcher, by the way. But you see this, there's some kind of, this patient is feeling uncomfortable, I think. Maybe I can show this, a little bit abrupt motions you can see. So let's just publish the second poll now, if possible, Dennis. So why do you think the walking support seems so uncomfortable for the patients? So what are your opinions? So maybe the robot is exerting so much power, or the person behind the robot human system, there is another helper. Maybe he was pushing the robot too much. Maybe the robot is probably not moving in a precise manner, right? Trajectory following problem, because you give some kind of walking commands, but maybe the robot is not able to follow them, or the robot is not able to handle reaction forces. Well, there are, of course, by the way, I really like this research. So it's not like I try to criticize this research and, this laboratory, I think they are the leading laboratory in exoskeleton development, Vander Poorten lab. But I just found this video very helpful to understand, to show, and they developed over this system a lot. So this is just an example, by the way, guys. Don't get me wrong, and it's my favorite lab right now. Okay, I think 40% of students, and maybe I can end the poll now. So we have, the robot is probably not moving in a precise manner. This is the trajectory following problem, or the robot is not able to handle reaction forces. So these are two close answers. I really like this poll right now because let's see. So of course, the person behind the robot is not putting so much force. I think he gently holds it. But the robot also, they control the power of the robot. So either the robot is not moving in a precise manner, or when the robot puts its feet on the ground, there are too much excess force. Maybe that's the problem. So let's see. Maybe I can end the poll. If precision is not the problem, guys. Maybe I can show you something. Because right now, in this kinematic, for example, even with simple PD control, like precision control is so easy, actually. We can easily make the robot walk. This is a very basic kinematic simulation, and using simple PD or PD plus disturbance observer, some easy technique, you can make precise the control. And oftentimes, I'm really surprised people try to publish paper and they say, we increase the joint tracking 0.1%. Precision is not the problem in most physical interaction problems. You can easily control the precision, but these are not pick and place systems. What happens is that if the robot is stiff, swing foot touchdown with no compliance, basically then, it's so stiff. But in human body, when you walk, you don't feel it, but your muscle impedance change. When, basically they absorb the shock, and then, your leg muscle impedance is softens, and then that's why you handle the interaction forces. But the robot cannot do it if you train it to do so. What happens is that if the robot is so stiff, even if you, as a human, a healthy human, if you wear this exoskeleton, you feel so uncomfortable. It's so hard to stabilize the robot. But what happens is that, normally if you have a compliance also at the robot joints or some sort of force control, basically these external disturbances can be, handled compliantly. So, for example, maybe this is not really obvious, but I show this video. Well, there are some data though, but I'm not going to show the data. So we have walking with an exoskeleton. So this is me when I was in Toyota Technological Institute. This was just a prototype. The exact same trajectories are applied to robot, but one with force control, which handles the ground reaction force, and one. Maybe from the video, it's hard to understand. So the right-hand side is no. But if you wear it, you feel this, comfort or, being uncomfortable much easily. What we do is also we collect data from the handler, so we can see how much the user needs arm force to stabilize herself. Or even with obstacles. So from the trajectory perspective, there is nothing different though, but right-hand side is, not handling the reaction force compliantly. Okay. So what happens is that, every time the human-robot combined system, touches down, there is this reaction force. And even if you train your robot to, reach this level, ground with zero velocity, zero acceleration, it is normally impossible due to modeling uncertainties. So you always feel the shock. But as humans, we never feel this shock because we, by nature, train our impedance. So our muscles basically softens at the moment of touchdown. This is maybe if you watch the babies when they try to walk, they walk in a clumsy way because they haven't understood how to train their muscles. But then over time, of course, this muscle impedance characteristics they develop and that they can walk stably. But the same thing has to be taught to exoskeleton. If exoskeleton is moving like a rigid system, every time it absorbs shock. So, but this applies not only exoskeleton, any kind of walking machine or any kind of system who interacts with the environment. By the way, if you understand, you can even harass the robot, by the way, which means that teaching your robot to become softer when it's needed, you can make sure that it can be stabilized itself. Here, for example, there's an exoskeleton, I push it, and every time I push it, it reduces the stiffness, so it becomes soft. So you can kind of think like a Bruce Lee, be water, my friend. Okay? So which means that when you hit it, to accept this external force, it just decreases its impedance, decreases its stiffness, so it becomes softer. So basically, you can harass the robot, but I harassed it with there is no human inside. Huh? So basically, then the next one, I will give the least priority to this one, but a wearable system should be designed with the human anatomy in mind. And I think today we have some nice talk from Ramazan Hoca, so he will explain this aspect more, so I will skip it a bit fast. But so maybe, you can just open your microphone and let me know the problem with this exoskeleton. So do you see any kind of problem right now? What kind of problem do you see in this human-robot connection? Maybe this is a hint. It's like
there isn't any knee protection.
Yeah, somewhat. But another thing is also there is this misalignment. So this is the knee joint of the robot, but this is the knee joint of the human. So, but even if you try to align, it's almost impossible because, the physiotherapists know that much better than I do. So, the knee joint, the rotation axis is not constant, right? Because there are some translation. And another thing is, for example, also if it's a shoulder joint, so we engineers usually have this fixed rotation axis, but look at this shoulder. the rotation axis elevates. We call it, I think, glenohumeral head elevation after some kind of range. So if you put a motor here, let's say exoskeleton, it has to also elevate together with the shoulder. So this is a little bit tough, not to crack, I think. But I will not give so much priority, and I need to save some time for Manu. And so basically, these are my take-home notes again. The system must be mechanically transparent. It must handle physical interaction and should be designed with the human anatomy in mind. So you can generalize this concept over the whole wearable robot. And can we publish the polls again? Maybe let's just answer the same questions. And it's very quick. Then we can switch to Manu. So again, let's just go back to the first question. Please answer it again. Like, I don't know if it became a little bit too didactic. So the first day, no harm. But if you are not convinced, feel free to ask me a question after Manu's presentation. Or okay, so pretty much everybody seems to be convinced. So the mechanical transparency is exactly that, because if the robot locks itself, obviously there is no motion, or if it exerts maximum power, basically it just forces you to do something, like it's not good. Obviously not watching Casper though. So yes, we got a great majority of people seem to be convinced. And can we publish the second poll again? So again, if you remember this, walking support video, the patient was experiencing some oscillations. Okay. Injector problem. So that's it from me. My second presentation will be on Wednesday. Now I would like to switch to, Manu will present the second. By the way, sorry. Thanks for your attention. These are the people I contributed for these videos. And the second portion, Manu will present. Let me just briefly, introduce Manu.
By the way, may I ask some very quick question before you go?
Maybe let's listen to Manu first, and then at the end there will be some time for you guys to ask questions.
Okay,
if possible. Okay, so Manu, I think he's a professor in University of Leuven in mechanical engineering department, and I believe he received his PhD from Kyoto University. So I kind of feel close to him. I also receive my PhD in Japan. So currently he's an associate professor at the Faculty of Engineering at KU Leuven, and he coordinates the robot-assisted surgery research group. Manu, thank you very much for your contribution. So, yes.
Oh, thank you. Can you hear me?
Yes, we can.
Okay. Yes, I shared my screen. So it's an honor to be teaching here in the winter school. It's only a short, brief introduction on collaborative robots that I'm going to give. I do have to apologize because I have a kind of a poll, but it's not in the official system. So I would like to ask you whether, first I'm gonna share my screen properly, if it's working out.
No problem though.
So the question is whether you could check, given this address in your browser, and whether you could see whether you can access this poll as well.
Maybe you can share it in chat window if Dennis can, enable chat. If possible.
Yes.
Or maybe I can quickly write it.
Just is this one here? Probably it could be. Where is the chat? Sorry.
No problem.
Here is the chat.
Manu, there is another link, respond@pauleve.com. There is another one? No, yeah.
I put it in the chat. Can you see it? Can you access this one?
Yes.
Yes. Okay, so it's active. So then we'll move to the presentation, and then I hope. So this is my talk gonna be. So first, gonna explain, ask you a bit for your input on your knowledge on existing collaborative robots, what it is. I'll briefly discuss the basics, and then I was asked to give some identification of bottlenecks and challenges.
I'm so sorry. Okay, Dennis wrote
yeah,
this.
Manu, we cannot add, activity unavailable, it says.
Yes,
Yeah.
because it's not started yet.
Okay, great.
Wait, it should be activate. Now it should be, wait, can you see it now or not?
Yes, we can reach the another links which Dennis and Özkan shared.
Okay, yeah, and this can be indeed answered. It's a bit difficult to answer already now, but okay, so it's work. Okay, so then, so I'm gonna show you 4 videos, and then the question is gonna be, which of these do you consider as collaborative robots? So here, this is the first system that's being used. This is used for pick and place. Here at the bottom, you see an instrument where you have a steerable tip that is controlled by an artificial muscle inside here, which is connected to a lever. And if the scroll wheel is moved, then this tip is bending. And this is another system that's being used. And then this is a telesurgical system whereby you're working at a console, and then you are, wait a sec, you're working on a console, and with this console you are steering this robotic system, and the motion of your fingers are being mapped to the motion of the robot that is at the distal part. So this is like 4 examples, and my question is, which of these would you consider as being a collaborative systems? So I'm gonna switch off the results. Here you can a number of those are collaborative and a number of those are not, or 1 or more are not. So I don't know if you remember the numbering. So this is 1, this is 2, this is 3, and this is 4. So here you can see, I'm gonna move to the next one, but you see in this case, there is quite some discrepancy in understanding of what is collaborative robots. And normally at the end of this talk, you will get a better idea of what is considered that. By the way, collaborative robots are also called cobots, or often used co-manipulation robots, which is expresses the field that you're co-manipulating this robotic system to execute a task. There are quite some commercial systems around, and so my next question is: are you aware of these cobots, and how many systems do you think that there are around? So I'm going to the next poll. That should be active, which we're going to see the results relatively soon. So compared to exoskeletons, you can appreciate from the beginning that in principle the systems is a little bit simpler than an exoskeleton, as the number of degrees of freedom that you're typically controlling with such a system is rather low. It's only most of the tasks in the real world are 6 degrees of freedom. Sometimes you want a few more to have redundancy, but in general you don't have like 20 or 30 degrees of freedom that you have to control. So that possibly explains why there are a bit more of these systems around. So here you see, for example, you can count, this is a small video, you can count the amount of systems. This is an interesting website, Cobotics World, where you can see an overview of all the collaborative systems. that are currently commercially available. So this just gives you an idea that for those who answered more than 50, they are obviously closer to the truth, because there are many, many around, and then these are only commercial ones even. Now, the reason why these cobots are getting more interest is obviously we want to automate and we want to improve efficiency in factories. Everyone knows that we can use nice industrial robots for that. Here you see an example of a industrial robot that is able to execute tasks very nicely, but that also is quite dangerous. So there are many reasons to consider these collaborative robots to be more efficient in programming. Small batches is one of the main reasons, and then there are also reasons in terms of ergonomy or precision that you can still have with these robots, which is, as you see here, this is an overview of the key performance indicators. You get an idea of what is currently available. So typically we're talking about these systems if the degrees of freedom are ranging from 4 to 7. Payloads can go up to 170 kilograms and a repeatability of 0.01 millimeter. This is like the range, the spectrum that you can see. This here to the right, you see the strongest one with a payload of 170 kilogram. And here to the left, you have a very small one, which claims a repeatability of 0.01 millimeter, which is obviously much better than a human has. So that explains the reason for considering this type of robots. There are two big branches. You have industrial. This is an example of that, and then many of those could be translated to medical. So here you have the same robot from, in this case, a German company that is actually also altered and modified for medical use. Obviously, this entails that the safety of this system has to be detailed very carefully, and that you have a lot of regulatory conditions that you have to meet. And so these systems are platforms that are designed for that. And so that's an extra feature of this system. So here you see this system around where the human is grasping this system, and then it has, for example, I'm gonna show a bit more. So you see here, he applies a force on it. You have a force sensor in the tip or in the joints, and based on these force commands, you can actually program the robot to do a number of tasks. Here, this is the robot moving an ultrasound probe over a mannequin for ultrasound scanning. So the system can follow a certain trajectory that is taught by this robotic system, and then it will display some kind of safe behavior. In this case, the contact force between the robot and that environment is being controlled. So you can appreciate also, this is a relatively rigid system. So this linked to the talk from Barkan, this is definitely a non-back drivable system. But thanks to the force control, its measures, it becomes possible to interact with it. In general, obviously, such non-back drivable systems come with a relatively good precision, so they can keep their pose very precise. Whereas there is also a branch of systems which are non-back drivable, which are back drivable, and where reaching good precision is a bigger challenge. So if we look at the basics of cobots, I'm sorry for this stuff, I'm moving it around in all directions. So the difference with a traditional robot is that now you have an energy exchange between this robot and this operator. So in a traditional robot, this is everything you want to avoid. In the case of a cobot, you actually want to ensure this interaction because it's more intuitive to interact with that system. And so as I indicated already before, we have a few ways to do that. The medical system that you saw is typically a non-backdrivable co-manipulator. We call it a parallel co-manipulator because the human is operating parallel to the robot together executing a task. We have backdrivable versions of that, and then we have also what we call series co-manipulators, and that's actually one of the examples that you saw in the video, whereby a part of the robot is being controlled by the robot itself, and a part is actually controlled by the human. So the small instrument that you saw with a bendable tip that we call a co-manipulator, whereby this co-manipulator is in series. Number of degrees of freedom are controlled by the human fully, the overall pose, and then distally you have this part of the robot that is being controlled. So if we look at the non-backdrivable co-manipulators, this is an example here at the right. Those become, the purpose is to control them so that they become backdrivable, and this is done through the control. So it's essential that you have a force sensor there, because without force sensor, there is no motion. And then if you look at this scheme here, it is actually this force that is being measured in real time. And then depending on the behavior that you wish to achieve, you're going to control the velocity position of this cobot so that you actually affect the velocity and the position of the operator itself. The alternative is a backdrivable co-manipulator. This is through design that is realized. So here in the right, you see such a backdrivable system. It's used for eye surgery. Normally, it just moves by the force of the operator. It cannot resist fully the operator, but it can apply some extra force on top of that. So in this case, for very precise motion, we add damping on top of this. So in this scenario, you have an opposite causality. So the velocity is measured of this robot, and depending on the velocity, you are going to apply a certain force on the operator to generate a certain feeling, such as damping or a virtual wall, let's say. This is an overview of how you do that. So by just looking at a robot, you can immediately analyze which are the components of this robot, and you can estimate and judge pretty well whether it is going to be a non-backdrivable or a backdrivable system, and how it affects the performance that you can expect from those systems. Here is an example of another non-backdrivable but series co-manipulator. So here the robotic instrument is physically positioned between the operator and the environment, and you have, for example, this system here. Normally the video shows this. So you have the human carrying the entire system, and then here you have a number of actuators. These are piezo-driven actuators that are actually controlling the distal tip. So the distal tip position is going to be determined by a series of human motion at one point, and then on top of that, the actuator. And this can be used, for example, to improve the positioning precision. Here, the actuators of these robots are controlled to filter out the tremor of the hand of the human. So that's also a feature that you can implement. So here you have a part that is backdrivable. The base of the robot is fully backdrivable, and then a part which is actually not so backdrivable, which is this distal portion. And then once you have such a robot, obviously any robot that you have, even if it's a cobot, you can control it autonomously as well, or you can control it in teleoperation and from a distance in that case. So that's a nice thing about these cobots, is you can use them in different ways as well. You can use them for creating virtual bounds to avoid hitting critical portions in the patient or in a factory, and you can filter tremor and so on. If you then link them to a tele-manipulation system, you can do even more features like scaling the motion, as there is no physical coupling anymore between the two robotic systems. I'm gonna move a bit faster through this slide. It shows you the different properties of these systems. A leader-follower, that's the new name of a master-slave system because of recently master and slave is not a very popular formulation anymore. And then co-manipulation system or handheld instruments, which are then serial co-manipulation systems. So let's move on to the challenges and bottlenecks. So first, we have a challenge that we have to ensure safe operation. So we have energy exchange between the operator and the cobot, which is also contacting the environment. Typically, this is a very complex feedback system where stable operation is not guaranteed. And so typically you have, for example, here, this is a variability that you can have in the dynamics of the operator. And you have even more variability if you consider the dynamics of the environment. And so if you have a closed loop system with all this uncertainty, there is a big chance of unstable behavior. And so in general, what people will be looking at is passivity-based control, whereby you see this as an element, a single one port. And if we can guarantee that this behaves like a passive system, a spring or a damper, then you can ensure that you'll have stable operation. Another thing that is challenging is to really get rigid behavior. If you have a backdrivable system, you want to use it in the to protect, for example, a vessel or something very critical, then you want to make sure that the user can move in that direction but should not pass that boundary. And so if you have such a backdrivable system, it's quite challenging to keep it at a certain, not penetrate a certain virtual boundary. So that's a body of literature research that is taking place to find out how can we generate rigid fixtures with these systems. Opposite, if you have like this system that's non-backdrivable, what is difficult here is to generate highly responsive behavior. If you looked at this system, you may have understood that it's actually moving relatively slow and that the operator actually applies quite some force to move it. So this is not really as intuitive as you want, and it's a challenge to get that very responsive. So that's each of these choices will have these implications. And then if you want to implement some virtual fixtures, for example, as you see here, you may be drilling with a drill inside of a bone. This is an example of it. And you may want to really have very precise cut at a certain distance. So you have a forbidden region. You need to somehow implement that region, and you need to make sure that the position of this region is adequate. So you have a registration problem. You have to define with very good precision this location of this region with respect to your robot frame. And so you may need to do some calibration tasks so that this forbidden region is positioned exactly. In many cases, your environment may be dynamic. So then this region needs to be updated in a dynamic fashion. So that's another challenge. Then another point is, for example, here you have a shared control system. You have a serious co-manipulation system. So the user is able to move freely the instrument in space. And on top of that, you'll have some intelligent feature that is then the co-manipulated part that automatically executes part of the motion here. This is just the user is able to move this instrument, and then the distal portion is controlled so that it's always perpendicular to the surface. So you're sharing the control in this co-manipulation system. So that the mental load of the task execution can be lower. So what is challenging there is, well, you're changing completely the way that people usually operate with these systems. So you have to find a way to make this change here, this automatic control, intuitive for the user, so that he or she doesn't know that it's actually happening. And another thing is you may have many features. You have a virtual fixture in one location. You may have damping, and you may want to switch between those features depending on your task. So it's very important there. A challenge is to, if you're adjusting the controller, your user should be aware of that. And so if not, this would cause mode confusion and you may have a poor performance in the end. And then finally, you also may want to, if you're using these systems to teach and to execute tasks, you want to learn this in a very efficient way. So you want to embed intelligence in your systems. So here, this person is trying to automate, is trying to teach, let's say, a task and a grasping task. So you want to demonstrate this task, but you don't want to do it too many times. And so we need kind of smart algorithms that are actually learning this task from demonstration by the human, so that the system becomes versatile and we can operate also without human involvement. So there is also this kind of challenge that is around. Okay, so this is a bit an overview of the main basics of co-manipulation systems, and I still have a few questions in the to check in how much you understood it. So my next questions are, what are the 3 types of collaborative robots? I'm not sure if you actually were able to follow that from the discussion. I'll let some people answer more. Okay, so since it's a very compact and fast talk, I think, and the question is quite tricky. We have quite some variability in answers. So actually, there is none of the above is correct at the moment. So we typically speak about serial backdrivable robots and parallel non-backdrivable robots and parallel backdrivable robots. So it's somewhere between B and D. Another question is, what are the main challenges for collaborative robots? Normally, you should be able to insert your insights here, although it's the first time I'm using this option. It should be activated, yes.
Yeah, activated.
Sorry for that. Can you type anything there, or is it not working? How does it work? Mode confusion, yes. Any other? You can also provide some other challenges that you think from your own experience are an issue with collaborative robots. Confusion, external optimizing forces. Yes. And then a last question is assume you would design a cobot for assisting with a writing task. So you have a child and you want, which has a disability, let's say, and you want to use a cobot to help it learn to write. What kind of co-manipulator would you envision of using? I'm seeing here a serial robotic system. I think that may be difficult. So you want a system, if you want to really help the kid, it needs to be able to write him or herself. So if you would use a serial robotic system, that would alter the experience and it would not be able to get free from that, let's say. So you definitely want to use a parallel robotic system, and depending on the, it's a bit a tricky question, depending on the type of let's say the handicap of the kid, you may want to opt for a back-drivable or for a non-back-drivable system. If you have a kid which has a lot of spasms, whereby there are large forces in play, you want to have a non-back-drivable system, because a back-drivable system would not be able to hold those forces. Whereas if you have a kid with a lot of tremor and does not have too much force output, you may consider a non-back-drivable system. Okay, so this is a rough introduction to collaborative robots. Thank you for your attention. If you have questions, feel free to ask, or we can also ask, maybe you can also ask questions to Barkan on his part of the talk.
Thank you very much, Manu, for your great talk. It was very informative. Okay, so basically, I mean, all I can add is like, you know, the project is about wearable and collaborative robots. So then they have share a lot of common features. Like one is back drivability, which I also tried to explain, and Manu had lots of reference to back drivability and force control. So when we think about robots, we usually think of them like, you know, bringing some object from point A to point B, but, you know, the physical interaction is really, really important. So if you have any questions, or by the way, if you would like to have some break right now, feel free, or if you have any questions, we are here before every presentation.
I have a question.
Yes, go ahead, Meli.
First of all, thank you both. I couldn't understand some part. Actually, it's not... okay, let me ask it. For this person, we needed to make the mechanism more compliant, so that we are actually trying to make this robot more like human, in the sense that when its feet touch the ground, it's actually a soft...
landing, yes.
Yes, soft landing. Can we improve our compliance? Is it a good idea to do that for maybe better feet health or for better ergonomics? Because I think our shoes aren't really helping with that. And yeah, what do you think about that?
I think physiotherapists can answer these questions much better, but from my point of view, there is also some kind of an optimal stiffness. So basically, if you make it too soft, then, you know, let's say, then it is harder to walk also. Like, you know, it will be too bouncy sometimes. I mean, I tried it on a humanoid, not an exoskeleton. We made it really, really, really soft springs. And at that time, every time it hits the ground, then you have lots of oscillations. Maybe for shoes, this may not happen. And I'm sure as a human, if I give you really, really soft shoes, maybe initially you feel a bit uncomfortable, but over time you also learn how to regulate your muscle impedance and cope with this extra softness, because humans can adaptively walk, basically. Like, but a robot, it may not be such an extremely good idea, because there is no, let's say, online learning process, unless, of course, you program it
that way. So usually there is an optimal way of, choosing this stiffness, this compliance in walking especially. And if you make it too soft, then it's difficult. But again, when it comes to shoes, I think I may not be the, best person to answer this question though.
Thanks. It was a good answer anyway.
Okay, thanks. Any other questions, or if you would like to, or any other piggyback? So the take-home message is basically the interaction is really, really important, because a great majority of first wearable robots are continuously interacting with human, obviously, and also this collaborative robot, especially the ones that Manu showed, the human is always physically interacting most of the time. So this is one thing. And to improve this physical interaction, back drivability or software controlled back drivability, and sometimes this, maybe hardware-based back drivability is also important. And in my case, I couldn't give lots of time to the human anatomy portion, but I think Ramazan Ünal will cover that portion a lot. So that's why I give this. And it's not just also for, in my case, walking systems. It's, it can be applied to any kind of robots that, need to interact with the environment. And or even from my own experience, I really have difficult time. I wear this exoskeleton because my PhD is on humanoid robotics. So I was working on walking, but just humanoids, not a wearable robot. Then as a postdoc, I started exoskeleton with the idea that, you know what, I can make humanoid walk. Why not humans? But it's, of course, and I realized it's not that easy, of course. Humanoid walking is not easy, but my point is exoskeleton walking is, of course, structurally different. Then I tried for the first time. I have really difficulty stabilizing myself within an exoskeleton. I remember this personal experience, actually.
Barkan, which are, according to you, the most promising commercial systems around?
Yes. No, yeah, that's about the exoskeletons, you mean?
Yeah, yes.
I see. It's a very tough question. So my favorite is right now the Atalanta exoskeleton or Symbitron from the, I don't know if it's commercial though, from Vander Poorten lab. They recently published Symbitron. So the point is that I will also mention it in my talk on Wednesday though. So a great majority of exoskeletons, they use crutches because they can put only limited number of actuators, only hip and knee flexors, because they try to contain the weight of the robot and the price. The complexity, they try to reduce the complexity. So, these are commercially available. I like them a lot. But then in my also research, I try to get rid of crutches. So try to aim for self-balancing exoskeleton in which we need to put more degrees of freedom. And right now there is, I think, the technologically advanced exoskeletons from France. I think Atalanta, the company called Vandercraft. So they built this, I call it actually a wearable humanoid because it has 6 degrees of freedom per leg and it can make SCI patients walk with no crutches, which is really, really, I think, advanced. I saw it also in Exo Berlin, this event. I couldn't try it though, but yeah, it is really, really nice. But other than that, most are doing the job, but to me, the crutch is a big problem. So that's the next step. And I think, and from the research, the new exoskeleton from Vander Poorten lab, Symbitron, it was a EU project also. It was really, really impressive. I saw it recently.
Okay.
Okay. So,
may I ask one other question?
Sure. If nobody's asking, sure. Go ahead, please.
Yes, sure. It's not totally about wearable robots, but right now I thought about Boston Dynamics Spot or Atlas, and of course it is an additional requirement to design legs with compliant feet, let's say. But is it advisable?
You mean like in the case of humanoids or?
Yeah, like if an humanoid robot which is not being worn by any person, if you are going to design this, are you going to try to make it again compliant?
Yes, you have to make it compliant, and actually those robots are compliant, but it's not. It doesn't really meet the eye when you watch the video. So when I say compliant, it doesn't have to be physical compliance, some kind of soft shoes for the humanoid. They also measure the reaction forces and act accordingly. So that also creates some kind of, that we call software controlled compliance or active compliance. Also, actually, in my also exoskeleton video, the robots are rigid, but we make it compliant through the use of force sensors and the software. So this is called software. In fact, there is no springs inside, or there is no soft element, but the motor acts as if there is a spring, like a virtual spring damper. So in those systems, I'm pretty sure, like also I talk to those people in conferences, they employ a different form of compliance control and angular momentum control, which is basically the integral of torque. So it's also indirect form of force control. So whether using physical elasticity or software controlled elasticity, which is like through the use of sensors, so you need to incorporate force control to handle interaction force.
Okay, thanks again.
And for maybe, I don't know, if you watch, there's this company from Konya, I really admire those guys. But they have right now, if you watch these videos, so they develop also some kind of quadruped, but it's subject to lots of oscillations. That's because they don't control the compliance right now.
I know that company.
Yeah, but that's the main problem, actually. They do everything well, perfect, but they just don't do the force control. This is my personal view, though. If we have another question, do we have another questions, by the way? I mean, I hope the state of the art was like, and major challenges was like informative to you guys, but the take-home message is basically we need to consider this environmental interaction capabilities of these robots. And then, of course, if you are not an engineer, there are always, things that you can do, like, for example, if you're an industrial designer, maybe in your designs, this is an aspect that you can consider, like, how you can, for example, place the elastic elements with the interaction points, right? Or if you're a physiotherapist now, of course, you understand my point, like, because you know that the humans regulate muscle impedance a lot. So how we can incorporate our designs. So I hope that this is not just to take on messages to engineers, but also to physiotherapists and biomechanics and researchers, and also the industrial designers. Okay, so I think, by the way, the program is a little bit packed because, we give 2 ECTS to those who officially register. So to, how can I say, to make sure that there is no problem in terms of regulations, basically we need to, give lots of talks, like lectures, and, make you work basically. So that's why the program is packed. So I hope you feel okay with that, but feel free to, freshen up yourself during this talks also. So the next talks